The very first thing when we start the case, we actually have to select how we want to create the case. And there are several modes here. There are two wizards, and you can create new case and open case. So let's talk first of all about these things. What is that? Because some of you, sometimes we get questions, what is eMMC, what is eMMC NAND, and so on. So eMMC mode, it's the mode for work with eMMC chips via eMMC adapters. We have adapters, eMMC adapters for working with live eMMC chips, and that mode is made for working with that adapters. eMMC NAND, it's again for work with eMMC chips, but with damaged eMMC chips. So it's not for good chips, but for bad ones. Or maybe you want to get more data out of eMMC chips from some garbage blocks, then you can use that eMMC mode also. And there are two classic modes. It's for new case, so it's for regular NAND case where you have some raw NAND chip. You can create new case, or you can open previous case. On this screen, we can see type of memory chips. From the left side, we can see raw NAND memory chips with the different packages, and from the right side, there are eMMC chips. So for those chips, from the right side, you can use either this mode or this mode. This mode in case if this chip is good and it's alive, and in case if the chip is damaged, you can use this mode. Here there are that adapters I mentioned before for working with this mode. All of them have the same pinout but different sizes, so that's why we have their 10 by 11 millimeters chips and so on. Next one, and those adapters are used for, these eMMC NAND adapters are used for this mode, eMMC NAND mode. And finally, for NAND chips, we can use adapters which you can see on this screen. It's a standard ISO P48 adapter, LG52, which we have in starter kit, and some adapters from standard kit. So that's our most popular adapters. Also, you may know that there are monolithic devices where you don't have standard pinout. So for those devices, we have monolith adapters. So once we detected what chip we have, we should select correct adapter for this chip, insert it into the reader, and then we should start to read. It. And it's actually very easy. First you select the reader, then you click to the button read memory chip, then you select configuration, and there you go. After this, it's necessary to check, to do visual test if you have good data. If reader reads normal data out of the memory chip, or there are some problems, maybe bad connections, or maybe wrong configuration, maybe some other problems, and it's necessary to do that visual test. I will show you later several examples how data may look like with the different situations. Now we'll just will follow through the whole procedure. So, and then we will discuss each step in details. So first we read ID, then we get configuration from database, then we do visual test. Yes, yes. Sometimes there could be two configurations for the same memory chip. By the way, do you guys all understand what is actually configuration? Okay, so let me put some attention on this. When let's let me share visual memory constructor and new case. So the configuration, it's a set of parameters of NAND chip, which the software VNR should know in order to read this chip properly. So different chips have different parameters. And when I say parameters, I mean this. So we have a database of NAND chips. This is the list of supported NAND chips. And if you select some chip, you will see the configuration. So this window is a configuration of this particular chip. And the configuration, it's a page size, block size, plane size, amount of planes, protocol of reading, voltage for this particular chip. And yeah, basically that's it. So that's the configuration. And as you can see, different chips have different configurations, different page sizes, and so on. Yeah, sometimes you may get the chip which is not supported, which we just didn't have in our lab, and we didn't add the configuration to database. So that means that you have to detect that configuration by yourself if you can do this, or you can just make a request to our support team and they will help you to do this configuration. It's possible to do manually here, but it's kind of complicated process. So yeah, in this webinar, we will not discuss it. So there is a database of that configurations. And when you click, let me insert some chip. When you insert some chip, you can click on this button, read memory chips. And the reader will send standard command to the chip, read ID. So fortunately for us, this command is standard, and if chip is good, if connection is good, the chip will gives you ID. So in this window, in this area, we can see ID. ID, it's like a name of memory chip. And it's unique. And the chips with the same name, chips with the same ID will have same configuration. So if we had this chip before and we discovered its parameters, its configuration, so of course we put this configuration into we put this into the database. And later, when you get the same chip, you can just read ID, and then the software will take parameters of this particular chip from the database and will automatically insert these parameters in here in configuration. I will tell you, I will show you a little bit later how to check if configuration is good or is not good. There was a question, what is this option here in settings? Disable automatic chip configuration. So it's just about this. If it's enabled here and you read memory chip, hold on. Yeah, it's here already. So it's about that when you read the memory chip, from the very beginning configuration here is empty. So there is no page size, there is nothing. And to insert these parameters in this window, you need to click on this configuration. And that option is just to make you no click this line. So it will automatically insert page size, block size, and plain size in this area. It's not about like reading configuration from memory chip or from something else. It's just to make one click less when you select the configuration. So we read ID, we click to the read ID, the software reads it, and then shows amount of crystals here, and normally regular chips have up to 4 crystals. So 1 crystal means that one physical chip has like 4, for example, in case of 4 crystals, 4 chips inside, and all that 4 chips connected to the same interface, I mean same legs on the chips. And that's why when you read the chip, you can't read all that crystals at the same time, because only one crystal is connected to the interface in some particular moment. So the configuration, one more time, it's a set of parameters for some particular chips: block size, plain size, protocol, voltage, and so on. When you put some chip which is unknown at the very first moment for the software will try to read ID, and if there is ID in a database, software will take the parameters from the database. Yeah, it's like another die crystal. It's another die. So this is what we do. Yes, this screens shows exact procedure. You select the reader, then you click read ID, and then you select the necessary configuration. Usually it's just one configuration. After this, we check this workflow. So non-chip reading workflow. First, you need to select adapter. We did that. Then you read ID and select configuration. We did this. And then we need to test configuration and make data quality test. Okay, little explanation of bus and plain, please. Bus, it's the bus could be 8-bit or 16-bit. It's some chips supports 16 bits bus, data bus, and other chips, usually chips, have a 8-bit data bus. So it's just amount of pins for the data pins. It could be 8 bits, 8 pins, or 16 bits, and the same. It's one moment chip can send 8 bits or 16 bits, and the plain. It's like a mount, some array of memory cells, big array of memory cells inside one crystal. So basically the chip may consist of several crystals, then crystal may consist of several planes. It could be 1 plane or 2 planes, 4 planes, and then plane consists of blocks and so on. But we don't deal with planes when we set configuration of memory chip not configuration, but the structure. We don't set any structure here like a plane. We have just a root, so all memory cells, and then the next level will be blocks. So we don't care about planes when we set structure. We just see it here in the configuration. Okay, now let's see. Now let's see how we do this visual test. It's a kind of hard thing to explain. It's mostly about your experience. So when you do this visual test, you need to open the dump in bitmap. You need to get like direct access to the chip and check how the data looks like visually. And after some time, after some experience, you will clearly see if you have good data or you have some problems with reading. It was really hard for me to find what good words for this slide, because there are many different situations, many different cases. But in general, when we check this data quality test, what we pay attention on? First of all, we pay attention on if we can see recognizable patterns with clear borders inside the dump. So if we can see some XOR patterns or service area patterns, some bad columns, then we understand that it looks like data is good. It looks like data is normal here, and we can proceed the reading. Also, it's a good sign if we can see the end of the page. Oh, hi, Sean. Nice to see you here. If we find some data error and then scroll page horizontally, it's good sign if we can recognize the end of the page. That means that we can read whole page, and most probably the data will be good. And also we should pay attention that on the artifacts. There shouldn't be some weird patterns, some artifacts in the dump. As I said, it's kind of hard to explain what kind of artifacts, what is artifact and what is not artifact. It all comes with experience, and after some amount of cases, you'll see that you will understand how normal data should look like and how bad data looks like. Yeah, and from the right side, I try to explain what is bad configuration or incorrect configuration or bad reading. So bad reading, it's when you see weird patterns, some artifacts, or too many bit errors, too many dots, or you don't see data at all. So that means that configuration is bad. That means that something is going wrong with this reading. Okay, now let's see several examples. I have here So let me select one more time the configuration. So it's here. I read ID, I select configuration, and now I just click on this button, save and close. So the VNR will apply configuration. And now when I click to dump viewer, I get direct access to the chip, and I can see what's inside of the chip. So now I'm going to some area where I see data, and now you see kind of good data, good pattern. It's a good looking noise, and usually XOR data looks like this. So when you found some area with the data, you start to scroll it horizontally. And once you found something like this, now you understand that this is our service area, right? And if you can see that clear borders and all, these lines, all columns go straight without any, shifts and so on, that means that until now it's all good. Then you can scroll it again, again, and again, more. And here you can see the end of the page. So this is how the end of the page looks like. We have data, and then usually it's nothing. However, sometimes it could be some, some pattern, but it will be the same type of pattern within whole dump. If you will scroll whole dump vertically, you will see the same pattern in this area. But usually we have just gray pixels here. Okay, so let me read the equation. Yeah, that's the Phison controller. So this is example how good data looks like. And by the way, about bit errors, we can't evaluate the amount of bit errors in this area because it's all looks noisy. We can't understand what bit should be 0, what bit should be as 1. So it's not possible to understand if we have bit errors in this area. And that's why we should scroll the dump to some recognizable pattern like this one. And then we can just scroll it vertically. And do you see this here? I think you see this small dot, 1 pixel, this one. So this is bit error. This is how bit error looks like. Why do we understand that this is bit error? Because we see that, it's all around this pixel, we have just white color, white pixels. It's zeros, right? And there is just ones. So that means that we understand that most probably we shouldn't have this bit here. And this is how bit error looks like. And if we have something like this, just one bit error, it's very good. It's a really great chip. Great reading. And yeah, after this evaluation, we see that everything is good. We can see recognizable patterns with clear borders. We can see the end of the page, and we don't see any artifacts. We don't see too many bit errors. This is a good example. Now let me show you some bad examples when reading is not very good. Okay, so I close this. There is another chip here. Same package. Okay, now I have new chip in the reader, and if I will try to read this chip with the previous configuration, of course I will get some garbage or I will get nothing. So I need to adjust the configuration. How will I do this? I will click to read memory chip again. Okay, and now it's trying to read ID, and it got ID. Or now I can show you what this settings does. You see now it's disable automatic chip configuration. It's enabled now. So now when I run this window, I have configuration here, which belongs to this chip. But in this window, parameters still belong to previous chip. Or if you create a new case, you will have here just ones or zeros. But if you uncheck this disable automatic here, so it's like you enable automatic chip configuration. So now if I read ID, well, actually it's supposed to automatically take these parameters from this configuration and insert it here. So this is what was changed. It has same page size, but a different block size, plane size, amount of planes, and so on. Okay, so that's the new chip. Now let's check the version of this software. It's 3.8 and the firmware it's 4.1. There is no 4x software. So I click to close and I can open dump viewer. And here, I don't like this already because you see there is pretty recognizable pattern here with these lines, gray lines, and there are white dots, and that means that dots most probably are bit errors. So let me scroll to here, and here it looks pretty okay. We can see some data now. Let's scroll it horizontally to check the end of the page. And here we can see the end of page, and some blocks have a really big amount of bit errors. You see this dots. So if you will read this chip in this condition with these settings, probably it will be a bad idea. Probably ECC will not be able to correct all these bit errors. And sometimes, especially for Samsung chips, you can try to play with the voltage in order to reduce amount of bit errors. And we can do this here in VNR on Fly. To do this, I will just drag this workspace window here. So now I see this window, and I have access to the reader. And I can change configuration on Fly for this reading. And several years ago, we found that if we decrease voltage for some chips, quality of reading may be better. So now it's 2.5 volts. And we have power for like a main power and data bus power. We decrease both of them. And it was 2.5 volts, now it's 2.3. It's kind of the same. Let's do one more step. It looks like now it's smaller amount. And the next step. And it seems to me that now it's better. And if we will do one more step, most probably the chip will hang. Yeah, you see now it's too small amount for the reading. So let's increase the power like this. And actually, let's compare this result with the default result. So we have 2.5 volts by default. You see amount of bit errors. And now I decrease it to 1.8. And I think that it looks much better. So this is voltage control. And you see that this block is pretty corrupted. It still has bit errors, but another one, for example, this one, it's almost clean. Let's check how it looks like with the default voltage. Still pretty good, but anyway, more errors. Okay. Let me show you one more example. This is micro SD card. So you see in this card, and I will use this adapter for this card. Okay. Let's again read ID. Selecting configuration. This is Sandisk. Save and close and check the dump. No, this chip is good. It's a Sandisk. We have this service area in the beginning. Then we have data area. Do you know what is this? What is this column? This is how bad columns looks like here. It's some chips have bad memory cells from factory. It's like if you will compare with the hard drives have P list, primary defect list, and that sectors are bad from the factory. And nowadays, the chips, NAND chips also may have bad memory cells from factory, and that controller just doesn't write data in those columns. So that's why they don't have data. It's like they still clean from the factory, because on the factory whole dump was filled by FFs, and when controller wrote data to this chip, when user used this chip, controller just kept that areas, and that's why we see it now. And it's good when we see it, when we see it, because sometimes those bad columns may look like XOR, and it's kind of complicated to remove them. So let's keep scrolling. Yeah, and that's the end of page. So that's one more example of normal configuration, probably normal reading. So that means that we can read it. By the way, another thing that you may check, especially when you are dealing with some monolithic device, you can check if you have access to whole capacity of the chip. For example, you see you have some micro SD card, and you know that it's 32 gigabytes, all right? So you need to check, you can check in configuration if you have here actually 32 gigabytes. Let me show you this on another example, better example. So have a look. This chip has 4 crystals, you see, and each crystal has 2 planes, right? And plane size, we pay attention now on real plane size, is this amount of bytes. So we can calculate the size of this chip. I will take this number. This number, then I multiply it by 2 because I have 2 planes. Each crystal has 2 planes. And then I multiply it by 4 because I have 4 crystals in this chip. And I get this number. So it's approximately 36 gigabytes. So user capacity is 32 gigabytes. And if you see that your the chip has really 32, I mean device had really 32 gigabytes, and after this math you get 32 gigabytes, so you may be sure that you have access to whole area in this chip. All crystals are available and so on. You will get full dump. But in case if you have device with 64, let's say, gigabytes, and after those calculations you get 32, that means that you don't have access to part of capacity. Usually it happens because you can't read all crystals. Like you can read crystal 0 and 1, but let's say here you have nothing, so software can't read those crystals, and so you read just half of the capacity. So that's thing also is good to check if you can read whole dump. Came back to visual NAND reconstructor. Yes, and the last thing I wanted to show you, it's I believe it's this chip. It's another micro SD card. This adapter. Let's try to read ID. Oh, and with this card, I can show you one more thing that sometimes you can see 2 configurations for the same chip, like this one and another one. And most probably, in most of cases, the difference between those configurations will be protocol of reading. They will have the same page size, block size, and so on, but protocol will be different. And difference will be like a DDR or SDR protocol. You see one is SDR, one is DDR. And we don't know in advance what protocol should be used for this chip. So normally we first should select DDR protocol and check what do we see in here in dump viewer. And if we will see good normal looking data, When I say normal looking data, I mean that we don't see 1 byte 2 times, each byte 2 times. So that means that DDR is a good choice for this chip. Because in case if you really have SDR chip, but you will read it as with a DDR protocol, so the reader will read each byte 2 times. And that's why you'll see each byte 2 times in the hex view. Also, you will see it in bitmap view, but you know it's more significantly in hex view. But if the chip is really DDR and you read it as a DDR, everything will be good. You won't see any, duplications. So here we see, I don't see any duplications. Each byte is going just 1 time. So that means that this chip is a really DDR chip, and I made the right choice. I shouldn't switch it to SDR. Yeah, I will show the duplications on another chip. But now with this chip, I wanted to show you another artifacts. So you see these columns and these stripes. It's like a shifted pages. Here, here. And have a look how end of the page looks like. So pages are shifted, and it's not good to read this page, to read this chip as it is. And for such situations, you can also try to play with a voltage control. Sometimes it may help. So for example, I have 3.3 volts now. Let me decrease it to 3 volts. It's changed a little bit. Now 2.7. 2.5. Okay, it's kind of better now. And 2.3. Yeah, and now it's much better than it was before. So for some reasons, this chip, here we have bad columns as usually here, and all the things we need to care about. But the good thing now that data looks much better. So because I can see clear borders of some structures of bad columns and so on. And the end of page looks quite good. So that means I can try to read this chip. So this is what we do, and this is what we mean when we say that it's necessary to make a visual inspection of data quality after you apply some configuration. You apply configuration and you check it there. Yeah, and now let me show you how SDR chip looks like with a DDR protocol. So let me insert some SDR chip. This one, for example. And read ID. And you see it's SDR now. If I read it as an SDR, it looks good, like this. But now let me intentionally set a DDR protocol. Same asynchronous protocol, but DDR. Okay, and dump viewer. And you can see that it looks like blurry now. And if you run HexView, you can realize that each byte now is repeated 2 times. C6, C6, 66, 66, and so on. So all bytes are repeated. So that's the approach how to select SDR or DDR protocol. If you have a choice, 2 configurations. First you select DDR, and if it works, then you're good to go. You just keep using it. And if you have something like this, you switch it to SDR, and then it will work good. So until now, we will discuss how to select, how to understand what memory chip you have, how to select adapter, how to read. And now we have a physical dump. And now we're about to run ECC and do page layout and so on. So what is ECC? ECC stands for error correction code. And this element in the visual NAND reconstructor, it removes bit errors from the dump. You could see that usually physical dumps have bit error, sometimes smaller amount, sometimes bigger number. But anyway, that bit errors exist. And ECC can remove them. How it's possible? How does it make it? The thing is that when controller writes data to the physical chip, it has, let's say, it made some transformations of data, and it has portion of data, 1024 bytes, and it has, of course, ECC engine with some ECC algorithm. It could be Hamming or Reed-Solomon codes that codes are outdated already, or it could be BCH code, which is most popular for now, or LDPC code, which is the newest code. So controller takes these 1024 bytes of data, and when one of those algorithm, it's just creates or calculates ECC checksum, let's say checksum for this data. And then it will write scrambled data, user data, and plus ECC for this part of data into the page. So probably you saw that pages, the page structure, that usually we have data area, and then after data area we have ECC. So that's the ECC which I'm talking about. This ECC controller writes to page. And then later, when we do data recovery, VNR can read user data from the page, then it can read ECC from the same page. And then using these algorithms, it can try to check, first it will check if this data has any errors. And then if there will be some errors, VNR will just try to fix that errors with the ECC code from the page. So this is how it works. When the chip works with the controller in the device, controller makes pretty the same things. As I told you, when controller writes data to the chip, it takes scrambled data, creates ECC, and writes it to the page. And then when controller reads data, it does the same thing. It reads scrambled data, it reads ECC, then checks if there are bit errors, and fix them with the ECC if it's possible. So in this area, in this matter, VNR does pretty the same things like controller did when device was good, when device was working. But you see that there are different algorithms and different code words for different controllers and memory chips. Code word, it's a kind of complicated stuff, complex stuff. You can go to Wikipedia and read in details about the ECC engines and so on. But it's mathematical stuff, math stuff, and it's hard to explain and to understand. In easy words, we can say that when it's necessary to run ECC correction, VNR will try to read this ECC and scrambled data and take from a database of VNR specially designed code word for this particular controller and memory chip. So there is another one more database of code words. And when you run auto detection for ECC, VNR is searching in that database good code word or correct code word for this particular device you are dealing with. Code word, it's it's like a formula which is used to calculate and to fix and check bit errors. To run ECC correction, well, first of all, it's necessary to select that code word, right? So on this screen, we can see what you need to do. It's just several clicks. You should bring to the workspace this BCH element. And then you should click to the find code words. This window will appear and it will suggest you some code words. And you should pay attention on this column, result. So if you see quite big result, quite high result here, that means that this code word most probably will be compatible with your particular case. And if you have several code words with the same result, you need to select the one which has same controller name. However, most probably that all these code words will be the same. I mean, as I told you, code word, it's like a formula. And if we will analyze that code words, analyze that formulas, we'll see that all of them will have the same numbers inside. And we have 3 of them because all those controllers, this one, and this one, they used the same code word, the same ECC algorithm for working with. So basically, there is no big difference which one will you select. This one, first one, second one. But if you know the controller name, you can just prefer the one which was made specifically for your controller name. And the code word, each code word has information about allocation of data area and ECC area. Data area and ECC area. So once we select some code word, some specific code word, VNR can automatically set borders of data area and ECC areas in the page. So once we find some good code word, correct code word, we can do page layout automatically, and you don't have to deal with that data areas, ECC areas, and so on. Everything will be done automatically, and you can just proceed. There is one thing you will have to do still. it's selecting LBN and the header. But LBN and header selection was discussed in the previous webinar, so you can watch that webinar. There's a description there. Well, usually here, as Sasha said, it's a little bit messy for now, but you know, in general, it's in file name, it's written controller name, then it's written page size. So for example, let's have a look in here. So we have our page size, and then we have number 4, which means that it's an amount of code words. It's kind of complicated. I said code word, but now it's a amount of code words. Actually, each line, it's several code words for this particular, because one code word explains one data area and one ECC area. So if we have page size 8 kilobyte, so most probably we have 8 data areas and 8 ECC areas. So this line, this like selection will have code words inside it. So this 8, 8, 4 means amount of code words. And also sometimes it's written ECC size. Like for example, here we have controller name, then we have our page size, ECC size, and number of code words. I don't know if Sasha wrote here in the chat, but we are actually trying to do some global database, which will have all the things inside. And it's going to be online database with the XOR controllers, ECC code words configurations, and all this stuff. And the software will take all these things from the internet automatically, and it will be all redone, and I think will be, you know, more clear, less messy. So when it comes to work with ECC, you need to do just several clicks. First, you bring ECC, then you run searching for code words, select the necessary code word, and in the end, the software will ask you if you want to do page layout, like if you add ECC parity areas to page structure. But basically, it adds ECC and data areas. I believe that we should change a little bit this message. And yeah, the previous webinar, we have it online. It's on our YouTube channel. You can just search on Rusolut on YouTube and you'll find it. All right, so now and let's say several words about page structure. Page structure, it's, you know, the structure for some particular controller, it's a pretty standard. For example, if we are talking about Phison, normally we have data area, then service area with a LBN header and other things. Then we have ECC, which protects all this data, like data area and plus service area. So it's in other words, it's a payload area, ECC, sorry, parity area, and this area, it's a payload area. So this ECC protects all these things. And then we have like a next period, next data area with the own service area and ECC for this data, and so on. And usually for modern controllers, data area has a size of 1024 bytes in case of Phison controllers, Phison, Silicon Motion, and another. So if we have like 8 kilobyte page size, we have 8 periods of data areas plus ECC and so on. In case of Silicon Motion, we have just one service area in the end, and within the page we have data plus ECC, data plus ECC. So just one copy of service area with a service area ECC in the end. And Silicon Motion usually also have 1024 bytes for the data area. So it's a standard value here. However, ECC and service area may be different for different controllers. Sandisk has a little bit another structure. The page starts from service area, then data area goes, and then ECC. So it's a little bit inverted here. Service area goes first. And knowing this structure, you can actually pretty easy to detect all that sizes and all that borders. Because data area, as I said, always 1024, or in case of SanDisk, it's 2048. Very old devices have 512 bytes of data area. But if you are dealing with pretty new device, with a not very old device, most probably it will be 1024 bytes for data area. So data area is constant within the page. And ECC area, but ECC area may be different for different controllers and different chips. And so you see the range, it's pretty wide. It's from 10 to 12 to 100 bytes. However, if you have some particular device and first ECC area is, let's say 42 bytes, that means that next ECC area will be 42 bytes, next one will be 42 bytes, and so on. So all ECC areas within of one device, some particular device will be the same. And spare area sometimes could be different even within one page. It's quite typical for Phison controllers. When first service area it's a little bit bigger than next ones. And you should pay attention on this. That first service area of Phison could be a little bit bigger. And yeah, it's the typical size of that service area. So now let's see how that automatic adjustment works. Okay, let me open some case. Yeah, for example, this one. This case, it's one of those which you could download from Google Disk. We did share this case with you. So you can try later to repeat the steps, which I will show you now. This is almost finished case and everything is prepared here already. There is no just one step here, it's a ECC. So we need just to finish it with the ECC. And let's see how do we do this. So there is a physical image, and let's say that we don't have it for now. We have just a physical image. The first step, if you remember, it was we need to bring here ECC, connect it like this, and now it doesn't have that code word, that formula. Now software doesn't know how to fix bit errors. So to find that code words, we click to this button, find code words. And a new window appears. To speed up the process, we can select specific controller if we know the controller. If you don't know, so we can run search by all vendors. By the way, that's the nice way, convenient way to detect controller name if you work with some monolithic device. When you don't know what controller you have inside, so you can run code word search through all vendors, and probably it will, some code word will be good for this device. So with this, you will just understand what controller you are dealing with. It may help you later. Now I know that this is a PS controller, Phison controller. So I select it and I click to the find button. And what is going on now? Now software is just trying to apply old code words for the Phison controller to this particular case. And once some code word is good, shows good results, we have this message. We have message about this here. And if we have like bold numbers, so you see that we have here 99%, but it's not bold. It means that code word is correct here, but page size is wrong. I mean, you see it's 4 kilobyte page size here, but this device has 8 kilobyte page size. So that means that for first 4 kilobytes is compatible, is correct for this device. But then these code words, they have just nothing. And those ones, they are good. They have code words for full page. Okay, so now let's select the one which is good and which has the same controller name like I do have. And now I click to the select. And if I didn't do page structure on physical image, so I didn't set page data areas, ECC areas, there is no structure on physical image. So VNR will offer me to add ECC areas and the data areas to the structure of the case. So I should click here on yes. And now have a look. I still don't have structure in here. You see that page is undefined on physical image, but on the ECC element, I suppose I do have it. Yes. So all that page layout step now normally is done automatically. Now once software finds a good code word, it offers you to set data areas and ECC areas, and it's done it for whole page. So you have here data area, then undefined area. What is this undefined area? It's actually the service area. Like here. Then we have ECC, then next data area, and so on until the end. So basically all you need to do here is just to set LBN and header. Okay, I can do this. Do you guys remember where is header and where is LBN of Phison controllers? Yeah, right, header. The first one is the header. It has 1 byte. Okay. And then LBN 2 bytes after 1 empty byte. Let me change LBN color. Like this one, for example. And that's it. That's all about page layout for now. So normally, if your case is supported, if we had this chip and this controller before, you don't have to worry about page structure. Yes, please, Amarbir, ask a question. Marbir, you are online. Ah, okay. You are not. Okay, now I cannot unmute you.
Yes, sir, I can hear you now.
Mm-hmm.
Okay, my question was that when we are adding anything into the structure on the extreme right hand side, where you say block is this much as block, page is this much as page,
Yes.
from where, when we add something into it, that area remains empty. I mean, if I add essay into it, it will not say as essay. How can we add that text at the back?
This text from the right side, it's from the left side you have names, and it's just a names. I mean, you can set here any name.
This is clear that, for example, if I want to add like empty, and I say empty is like 1 byte, and then after that I want to say as empty, but I can't write as empty over there. Why so?
Yes, I was trying to answer you. So, and from the right side, we have structures. It's like a standard structures which our software knows what is it. It's like standard structures for the software. So from the right side, from the left side, we have just a names, and we can put any name here. And from the right side, we have structures which software use for work with some particular device. And here you can see list of structures which are necessary, which is necessary for the software. So there must be structure, block, page, data, area, and so on. And for example, you can, let me edit structure, take this number. If I will delete this structure, remove structure, right? And now I will add new structure. I can type anything here. Name will be anything. Size, let me set the correct size. And now it's anything. And software has no idea what is this. But then when I do right click, I can set this anything as some kind of standard structure which software is used for work. So we remember that this anything, it's actually block, right?
Okay.
So I can set this as a block structure. So now this anything, it's a block, and now software will know this line, this string, it's actually a block. And you say that you can't set this as a empty byte or as a essay. It's just because such structures, that structures just do not exist for software. Software doesn't have the structures, doesn't use the structures.
So only the standard structures have this text written, like as data area, as ECC, as header, as LPN, right?
Yeah, right. Because here you can set any structures for, for your own purposes. For
yes,
sometimes it's necessary to add some, specific structure. But for software must know where is data area. For example, you can set here, you see now data area is 512 bytes. You can set like add structure, one more data area 1, for example, and you will set 1024 bytes. But software will ignore this line. It will not take into account this line.
I have understood this totally.
Just for you. It will work with this. But if you want to switch using this for software, using this data area to this one, you need to make it like this, set as data area. And now software will not use this structure, but will use this one as data area.
Correct. Thank you.
You are welcome. Okay. So it looks like I kind of corrupted structure here. Let me fix it now. So you see now I can set this anything as a block, because I do remember that this is block. Okay. And now here I should set page to 56 pages, and then data areas. And I need to switch back this data area, set as data area structure. Sometimes there could be, some people can do mistake, because even though you have some structures are described here, for example, like now, we have this like a green data area here, right? And you may think that everything is good, everything is all right, but software will not work, because in fact, for the software, data area is this structure. And there is no this structure, you didn't use this structure anywhere. And the software will see that there is some data area, but it's not used. And you will just not be able to proceed with some next steps. So you should pay attention on this. Now I will set this data area as a data area, and I will delete this one. All right, so now it seems to be better. Okay, after you selected, code word, it's necessary to check it. And to check the code word, you can run ECC map here in parameters. And if you see these beautiful green colors, that means that code word is correct, is good for this case. So if you see dark green, that means that, yeah, one square here, it's one page. So if you see dark green, that means that this page doesn't have any errors at all. If you see light green, that means that there are errors, but ECC can correct them. So after ECC correction, it will be good. But in case if you, let me damage this code word. So yeah, by the way, here we have list of that code words, and I can damage it a little bit like this, for example. Now it's incorrect. If you see something like this, that means that this code word is not compatible for this particular case, and it doesn't work. The number here just shows amount of pages in this line. So now it's 32 pages. If you, now it's 14 and 1. So just for, you know, better convenience. Okay. Now let me select code word, normal one. Okay, so when you see this map, you understand that you can proceed. And let's go back to this case. We connected, we apply XOR, blah, 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 markers table, work with markers table. I think these two steps will be discussed in some next webinar, if you will still like it. Okay, then we click to create logical image. And there you go, file system viewer. Photos, and if I open photo, you see it looks like this. So this is how bit errors look like. And why do I still have these bit errors? It's because ECC is off now. So ECC doesn't correct any data, it just passes through all the data, and here and there you still have that bit errors, and physical image still have that bit errors. yeah. The same aquarium. So to enable correction of ECC errors, like to enable on-fly correction, you can just click on this button, power, and now if you will open this picture, it's good. So that's it. That's all you need to do when you work with the ECC. And it's good when ECC can correct all these bit errors. But sometimes it can't do this. And in that case, you need to run dump rereading. We will talk about dump rereading a little bit later. Now just let's see one more case or several cases. So I will open another case, this SM. So I have physical image and I will do pretty same steps here. So first of all, I bring ECC element to the workspace. It's here. Then I run codeword. Oops, not this option. Find code words. And it was a SAM controller. So I select this. And it found 4 code words for pretty different controllers, some of them. But I believe that all of them will be compatible because result is the same. And if you point mouse on some code word, you can see numbers, arguments of that code words. And you can see that all of those code words have same numbers. So basically you can select any. But just to make it right, let's select the one with the same controller name. So select, then it asks you if you want to add parity areas. Yes, you do. And there you go. You again have here data area ECC. And if you remember, ECC, Silicon Motion controllers have first data area plus ECC and then service area in the end. So that's why data area plus ECC go in row. And then here we have the service area with its own service area. Okay, now I connect it to the next steps. Click to create logical image. And there are data. There are files, there is data here. Okay, and the last case, no, it's not last. There will be 2 more. So AU controller. So like this. So I repeat it like normally. You find okay. For this controller, there's just one compatible code word. I will select it. Do I want to add data area plus ECC? Of course I do. And now let's see the structure. Okay, so AU controller has 1024 bytes of data area, then 2 bytes of service area, and then 112 bytes of the ECC, and so on. The page has size 16 kilobytes, so we have here 16 periods of data area plus ECC. So after this, I just connect it like that, check the data. It doesn't work, but if I enable ECC correction, it will work. You see, this device is really corrupted. Has a lot of red pages, but still most of the pages have a light green. So it means that ECC still can correct it. Yeah. Okay, and let's see. And there is data here, and I can even see it. So ECC was working good until now. And I didn't have to do any other steps to get the data. But now let's see the next case. Open case, no. This one, Sandisk. Let's don't see this now, and let's concentrate on this solution. So it's a standard situation here. We have a physical image from Sandisk. It looks pretty normal, pretty okay. Now let's run BCH or ECC correction, ECC search. So I click to find code words, select Sandisk, and click to find. Okay, so let's select, for example, the first one, select add ECC parity areas. Yes, we want to add this. Let's check the map. And again, there are some red pages, but most of pages have light green color, so probably it's good. It should be good. And then I connect it like this, create logical image, try to open file system viewer, and yeah, let me run ECC. And it cannot find anything. So even with ECC enabled, I don't get file system. And it's pretty regular case because usually memory chips have pretty hard corruptions, big corruptions, a lot of bit errors. And it's a really rare case when you can get all the data just after first reading, just after first reading and ECC, one ECC correction. So for those cases when, let's say, the device has hard corruptions, many bit errors, we can try to use such a thing like dump rereading. What is that dump rereading? It's the procedure when VNR will try to read one more time these pages which have a red color now. So the pages which can't be corrected by ECC right now on this step, I mean with this data or physical image, those pages VNR will try to read one more time from the physical chip. And there is a pretty big chance that on a second try, or maybe third try, fifth try, this page will be read correctly, will be read good. And now let's see how does it work. So basically, we have many places where we can run that dump rereading. We can run it on ECC element. Yeah, let me tell several words about options that we have here on the ECC element. So we have our option to correct dump, reread data blocks. So correct dump means that ECC will correct physical dump by ECC. It will not try to read anything from the physical chip. It will just work with the physical dump, will work with the ECC, which is written on that physical dump, and we'll try to correct the chip. Because as you saw, when you get the physical chip and then you turn power on, ECC doesn't change anything in physical chip. It just corrects all data on fly. And here we still have bit errors, and here we have corrected data. But original data is not fixed. It still has bit errors. But if you click on this button, correct dump, it will run correcting of the dump. It will just rewrite dump and fix all bit errors which is possible to fix. So that's the first one. Now you see that the color is changed now. So it was light green, now it's dark green, because these pages, they don't have any bit errors anymore. But as I said, sometimes it's not enough just to correct bit errors. Sometimes it's necessary to try to read again dump. And we can on the ECC element, we have two options. We can try to read pages with unrecoverable bit errors within whole dump. So whole dump will be, well, with this option, it will actually do two things. First, it will correct bit errors of pages where it's possible to do so on light green pages, and on dark green pages, dark green pages will be read again from the dump. And with this option, reread dump, it will do this on whole dump. And the last version of utility can do pretty the same operation, but on data blocks only. And this operation can work much faster than previous one, because if you have quite big chip, and but the amount of data, it's quite small, so you don't have, or user didn't have a lot of data on that chip. If you run this first option, it will try to read whole dump, and if the dump is big, it will take a lot of time for this. But second option will try to read data blocks only, so the blocks which really have data. And how software can understand that where are data blocks and where there is no data blocks. Yeah, data blocks means here not data areas, but the block, physical block of the chip, which has user data. And it works with the devices which use XOR transformation. So when you did first reading of a physical chip, software analyzed on fly what kind of data is going on through the reader now in some particular moment. And each block was analyzed, and software made decisions like this block has data, this block doesn't have data. And so later, and after the reading, software has like a map of blocks with the data, with user data. And with this option, you can just pretty increase speed of rereading. It will not read whole dump, it will read just the data blocks only. And as I said, it will work with the cases with XOR transformation only, because we decide what blocks have data by testing entropy, and if entropy is high, then this is data block, and we try to read it later with this option. And if this is empty block, then entropy will be low, and this block will be not marked as a data block. Also, we have that dump rereading options in two more places. In markers table, you can try to reread it will try to read the blocks which you selected in markers table. So when you create markers table, you select some blocks which will go to logical image, and you run select some blocks which will not go to logical image. So you do the things which we discussed on the previous webinar. And if you understand that you want to read that blocks in markers table, you can run this procedure with this button inside markers table. And the last place where you can run that rereading, it's in logical image in file system viewer. You can try to read allocated space, and it will read allocated by file system area sectors. You can try to reread unallocated space, or you can try to reread selected files data only. So you have many options where you can run this rereading, and it's up to you which one to select, which one to choose. Do you still hear me? Because I get message that internet is bad. Okay, great. So let me proceed. It's up to you which option to select, how you want to reread the dump. If you want to reread the dump right in the start of your case, so you can do this on ECC element. You can just reread whole dump, or if you want to speed up process, you can read data blocks only. If you want to do this later, if you can create markers table, if quality of dump more or less is good, you can do this later on markers table. You select blocks which you want to read and you run it there. Or you can do this on a very last step for some particular files only. For example, you have a quite normal dump, but some essential files are bad. You can't read them. You see bit errors, probably bit errors on that files. So you can select that files and try to read pages of that files one more time, and maybe it will be better. And when you run dump rereading on here or on last step, you will get this window. And as I said, software will, first of all, it will correct all light green pages by ECC, and all red color pages, it will try to read several more times from the chip. And there is possibility that on next tries this page will be read better. And there is one more thing. Okay, let's first see. No, let me add the last thing. That for some controllers, sorry, not controllers, but memory chips. For some memory chips, we have read-retry tool, and this read-retry tool, if it's supported, does pretty amazing job for the reading, because it will try to read these red color pages with some, let's say, advanced mode with another thresholds of 0 and 1s for each memory cell. And for many chips, it will bring much more data. So what is read-retry? Several words about read-retry. Here we can see one memory cell. And how does memory cell keep data? There are several thresholds, and each threshold means some data. For example, if the voltage like 2 volts, some memory cell has 2 volts, that means that it has 1 data. If the memory cell has bigger voltage, it will be 0 1, then 0 0, and for example, if it has highest voltage 2.9, it's the data is 0 1. It's a structure of MLC memory when one memory cell may have 2 bits inside. So that's a normal memory cell with the normal thresholds. So this is one threshold, next, and so on. And the good memory cell has these thresholds like it was like from the very first moment, from the beginning. But the thing is that after some time, some memory cells may lose its charge. And for example, if it was in the beginning 2.9 and 3 volts, after some time, two of these memory cells may lose charge. And if it was 0,9 before, now it's a 0,0. And if we, originally, it was data BE, so 0, we had here, have a look. First cell, it has 1, 0, then 1, 1, 1, 1, 1, 0. This byte, it's BE. Then after some time, two memory cells lose its charge, and now it's with the default read, we will get bit error. We will get 3C instead of BE, because these two memory cells will bring us data 0, 0 instead of 0, 1. And so with the read retry, we can, with default read, we will use these thresholds, like original thresholds for these memory cells, for all memory cells, default thresholds. But when we run read retry, software VNR will try to move, will send special commands to chip, and chip will move that thresholds, and we can adjust the thresholds for new situation. So we shift them, that thresholds. It was original charge of that cells and default threshold. Now we shift it, and on first attempt we can get this memory cell, and then we get we made one more shift, and we can read now these two memory cells normally, and again, and we can get original data back. So this is what read retry does. Basically, just shift thresholds in order to get data from memory cells that lost its charge. And how to run that read retry? It was really hard, and it took us a long time to develop all that automatic adjustment things. And now you don't have to do anything. If read retry is supported for this particular chip you're dealing with, then you will see here like read retry algorithm 9 now. And you understand that read retry is supported for this chip, and software will automatically apply it. If there is nothing here, then read retry is not supported. So probably you can try to contact us, and we will try to figure out to develop algorithm for the read retry for your particular chip. So that's actually all about dump rereading and read retry. Now let's see how it works. So if you remember, I told you that I showed you this case before, and the normal ECC correction didn't work. We didn't have data here. You see, I ran ECC correction, now file system viewer, and it can't find anything. So now let me run that dump reread option. This read data blocks is not available now because I probably imported this dump. So to have this option enabled, you need to read chip first, and then software will create map of the chip, of blocks, of all blocks, and then you will be able to read data blocks only. But this case is kind of artificial. I didn't read it before, so we don't have this map. So then let's just run whole dump read. So I click to this button. Yeah, and we get this window. I can just click to the start. Yeah, and I don't have chip connected. Let me connect the chip. Yeah, of course, when you try to do this read retry, chip must be connected, because it will try to read these bad pages from the chip. So ECC read dump start. Cert, yes. And now it's trying to apply several parameters for read retry, and when the parameters is found, you see that it's starting to correct. And here you can see the statistics that empty blocks, it's this amount of blocks, good blocks here, correctable blocks is here, but most interesting part is here. So until now we got 155 or 200 blocks, bad blocks, and software tried to reread what's already 400 blocks again one more time from the chip, and 120 blocks now are good, so they were read and now they are good, but 400 still not good, and it's on first try. We do this reread operation several times, and maybe on several try, on third try, on fourth try, we will get more and more blocks corrected. And of course, it will take time. So here, I have one more image. And on this image, I waited until end of the procedure. So I passed all that reread operation fully. And now let's try what result do we have now after this. So this image, it's after rereading. Same image, but after rereading. So find code word, selected, add parity errors, yes, create logical image, and it should be corrected. And file system viewer. And we have the data now. So this is how read retry works. I want now to try to open case, another case where read retry works even better. So have a look. This is micro SD card with a Phison controller, and it's hardly corrupted. And now let's see how can I run that reread operation. So if you will try to read the data, all the data will be corrupted. And here there is a map of blocks. I can run option to reread data blocks, and actually also I can select all ECC elements and run this reread data blocks for all elements. So it won't be necessary. It will not be necessary to like run this for first element, then wait until end, then run it on the next element. You can just select all of them, run this, and keep it working within night, several days. It will reread for all chips. So I select all ECC, reread data blocks, okay. Retry is supported for this chip. And now I click to the start. I need to set the chip. I think it's this one. Okay, retry parameters found. And have a look. It's like 60 blocks, 70 blocks, bad blocks, and all of them on the first attempt to reread become to good. So it's not just 4 blocks not corrected, and already almost 200 blocks are corrected. So basically all red pages that we had before now were turned into green color. So this is how retry works and reread procedure works.